In this lecture, we will discuss the two nucleon problem in terms of the bound states. So it turns out that you have three possibilities in the case of nucleon system, because there are two kinds of nucleons. You have an NN system, PP system, and an NP system. And for a bound state, of course, there has to be a nodeless wave function, which means L equal to 0, and that is usually the lowest energy bound state. Now, experimental data tells us that we don't have any PP or NN bound state. Okay. On the other hand, the NP system does have a bound state for S equal to 1, which means the two spins are aligned. However, there is no bound state system for S equal to 0. Okay. So, there is no partner to the S equal to 1 state. So, of course, the NP system which is bound has T equal to 0. It's a spin symmetric and spatially symmetric system. So, it has to be anti-symmetric in the isospin space, and that is therefore the T equal to 0 state. These are this is a summary of the properties of the deuteron, which we will of course try to understand in terms of wave functions and so on. So, the properties of the deuteron from experimental data is that it is a oh, there is a mistake here. It's a J pi equal to and T. This should be 0. So, it's a 1 plus J pi state. So, it's a spin equal to 1, total spin equal to 1, positive parity, and the isospin is 0. The binding energy has been measured to great accuracy. Of course, what is it's enough to know that the binding energy is small relative to other heavier nuclei, the last nucleon in heavier nuclei, and this is about 2.22 MeV. The magnetic dipole moment is about 0.86 in units of the nucleon or the nuclear magneton, mu n. For instance, this is smaller than that for the proton. The electric quadrupole moment is not 0. In fact, it is finite. Although it is small, it is still finite. It's about 0.286 E Fermi squared. The radius is of the order of about 2 Fermi. The electric dipole polarizability has also been measured. It's about 0.70 in some units with an error of about 7% Fermi cubed. So, let us talk first about the NP bound state. Now, the NP nuclear potential is of course very complicated, as we saw in the earlier lecture. It has many terms to it. However, a lot can be learned by assuming a very simple central potential. So, a potential that just depends on R, does not depend on the spin and so on. Okay. And the tensor interaction can be just considered to be a perturbation. Why is that needed? We will come to a little later. That is basically is needed because you have measured a small but finite quadrupole moment of the deuteron. So, let us start first with the central potential. Suppose the potential is defined by V of R equal to minus V0 for R less than B and is equal to 0 elsewhere. So, for the L equal to 0 S wave of the Schrodinger equation, the radial wave function can be written down as U of R by R, and this can be written down in terms of the Schrodinger wave equation. And so, this is just given here. This is the operator, and okay. So, if you try to solve for this, and the d is defined there. So, d squared of u plus k squared of u is equal to 0 for r less than b, and d squared of u minus kappa squared, this is something wrong. This should be for r greater than b. So, this is, it needs to be checked what these signs are. So, there is a wave function inside of the well and there is a wave function outside of the well. Okay. So, this is r less than b is correct. This should have been r greater than b. Okay. So d, as I said, stands for d by dr, and k is defined here in terms of mn by h cross squared. Uh, Kappa is, again, there should be a, I think there should be a square root because this sign doesn't match. This should have been a square root here. Lots of typos in this. Okay. And the kappa is defined by this mn b by h cross squared, the square root of that. Mn is the nucleon mass, b is the binding energy of the neutron. So the wave function can be written as u of r equal to some constant times sine of kr for r less than b, and b times some, again, some constant times e to the minus kappa r minus b for r greater than b. Okay. So it's basically an exponentially decaying wave function, radial wave function for radius larger than the range of this potential, and it's a sinusoidal one for r less than b. So you can fix a and b, these constants, by matching the wave function and their slopes. You can take the logarithmic derivative and match them, and at r equal to b. And if you do that, then you get this condition: k times cotangent of kb is equal to minus of kappa. You can also normalize the wave function. Psi of squared all over the radial space is equal to 1. So you get this condition: 4 pi times u squared times dr, the integral of that is equal to 1. So you get this condition: a squared by 2k times kb minus 1 by 2k sine k sine of 2 kb plus b squared by 2 kappa is equal to 1 by 4 pi. So then you can use condition 1 to eliminate a, and if you do that, then you get b is equal to this expression, which is dependent on the kappa as well as the k squared and on the range of this nucleon potential. Similarly, you get a, which is given by this expression, 1 by sine kb times kappa by 2 pi root of that, 1 plus kappa squared by k squared, 1 plus kb, and then the whole thing in the square brackets to the power of half. Due to the low binding energy, kb is almost like pi by 2. So you have a wave function which basically goes like this and then is matched to a wave function which is exponential decaying. So this is b, and this is for r greater than b. Okay. So you can fix then the value for V0 b squared, and that turns out to be about 100 MeV Fermi squared. Okay. So you can have a different V0, but then the b is constrained by this relationship. Similarly, you can have a preferred b, let's say, but then the v is constrained. So for instance, if you took b to be about 1.4 Fermi, which is kind of the pion Compton wavelength, then this V0 turns out to be 50 MeV. If you take b to be 2 Fermi, then V0 turns out to be 25 because of the square dependence on b squared. So then V0 is just 25 MeV. And you might recall that this kappa, which is given by this, because the binding energy is known, nucleon mass is known, this comes out to be about 0.23 Fermi inverse. So these are the radial wave functions for r less than b and for r greater than b. Now a substantial part of the wave function exists outside of the potential, and of course to some extent that depends on what the value of b you take, but for reasonable values of b, which we have listed there, 1.42 Fermi, then the RMS radius of the neutron can be calculated with just a expectation value of the r squared, and that turns out to be about root mean square radius of the neutron turns out to be about 3.8 Fermi, which is fairly large as compared to the size of the nucleons. So these are plots of the radial wave functions, u of r here given by this, and then phi, which is just u r of r by r for the square well potential. Now, if you take realistic potentials, then these differ somewhat. So, for instance, in this case, this is taken from the reference of Hyde, the textbook, Basic Ideas and Concepts in Nuclear Physics. So, the radial wave function u of r and V of r times cosine and sine of omega for hard core and soft core Reed potentials with normalizations, so and so. They are given by this. Okay, so one is this U of r and this is V of r. Okay, so now we come to measurements. So measurements concerning the deuteron. So of course, the electron scattering on deuteron has been measured, and this has been this is taken from a review article by Frua and Papanikolas in the Annual Reviews of Nuclear and Particle Science, 1987. This is the reference which is given here. So what is the graph taken from that review paper, work done by essentially by them. This is the threshold electrodisintegration of deuteron by electron at back angles. Okay. So EE prime and PN. So the deuteron disintegrates. So this is cross section, the differential cross section, d sigma by d omega over energy per unit energy d omega in terms of centimeter square per solid angle per MeV. This is given, this is plotted here as a function of q squared, the momentum transfer. So up to about 30 or so q squared. So q you can see is of the order of about 5.5 Fermi inverse. So this cross section of course changes by almost like 6 orders of magnitude, and you can see that the dots with the error bars are the data, and if you just take the deuteron to be consisting of a neutron and proton, so nucleons only, then this is the angular distribution that you expect from theory. So you can see that this is widely off as compared to data. Okay. On the other hand, if you take into account virtual pions that are there in the deuteron, then this fit is somewhat better. Okay. It follows it all the way up to about 12 or so q squared, and then of course it deviates. And finally, of course, if you include not just virtual pions but also virtual rho mesons and virtual delta resonances in the deuteron, then you can fit this reasonably accurately. Okay, this threshold electrodisintegration data. So it just shows that the deuteron, while broadly speaking it does consist of a neutron and proton, but if you look at particular aspects, if you look at the finer aspects, then you see that you need to include finer effects like virtual mesons, virtual excitation of nucleon to a delta and so on. Similarly, what is plotted here, again this is taken from the review article. If you plot the magnetic form factor in terms as a function of q squared, and here this goes right up to about 70 q squared, so that is about 8.5 or so in terms of q in Fermi inverse. Then you see the magnetic form factor, this is the experiment, the dots show the experimental plots with the error bars given here. Again, in this case, a certain model which takes into account various meson exchanges and so on, that gives a much better fit. And in fact, that meson exchange model includes a d state contribution in the deuteron, which means we have assumed that the ground state of the deuteron is just a s state, but there can be, because of the tensor interaction, there can be small admixtures of the d state, which means the L equal to 2 contribution. And you can also see why higher L contributions will not contribute, because of course the total spin that you have at your disposal is only 1. The neutron and proton are aligned in terms of spin, and so J equal to 1. Now, if you have let us say of course it has to be even parity, so you can only have S, D and G. So then the G means L equal to 4, but you can't couple a 4 to whatever maximum spin that you can get, anti-align and so on. You will get, you can't get a spin of total spin of 1. So obviously G and states and higher cannot contribute, so it only has to be a D state. And in fact, some of these models give a admixture of the or admixture probability of the d state to be of the order of 5% or so. In fact, some of these models also can estimate what is the delta-delta contribution. That means the neutron-proton can both get virtually excited to a delta resonance, and of course you can match the spin and so on as a spin. So that contribution is of the order of 1%. It's smaller, but it is not zero. Okay, so now we come to some of the static properties of the deuteron. So the magnetic moment of the deuteron is defined in terms of this operator, the expectation value for the when the substate m is equal to j. Okay, so the m substate is the maximum value that it can have, and in that you can take the expectation value of the magnetic moment operator, m1 operator, and for the deuteron, this is of course the sum of the two magnetic moments, mu n plus mu p. You can define the magnetic moment in terms of so-called G factor, which is the gyromagnetic ratio for a state of spin j, and mu n is the nuclear magneton, which is defined in terms of EH cross by 2 mn c, where mn c squared is the mass of the nucleon. So you can take the average of the proton and the neutron, and so it's just E times H cross c by 2 mn c squared. So this is the definition of the nuclear magneton, and so if you know the magnetic moment, you know of course these quantities, you know the J of the system, so you can extract the so-called gyromagnetic ratio. In general, if a moment m is there, then you have two contributions to the magnetic moment. So you can put a effective Gj gyromagnetic ratio in terms of mu and j, and a G1 and G2 coming from the J1 and J2 contributions, where of course you have to multiply of course by the mu n, the nuclear magneton, and J obviously is J1 plus J2. Now you can take the scalar product on both sides, you can substitute, and then you get a Gj into J plus 1 is equal to G1 j into j plus 1 plus G2 minus G1 times J2 dot j. So you can extract, if you go through this algebra, the Gj is just average of G1 and G2, where G1 and G2 represent the nucleons contributing to the gyromagnetic ratio, plus a G2 minus G1 times a J into J2 plus J2 into J2 plus 1 minus J1 into J1 plus 1 by the 2 times J into J plus 1. Now for a deuteron, the G factor is just given by half of this, because of course J1 is equal to J2, so this goes out, this drops out, so the second term is 0. So you get just half of Gp plus Gn. So the magnitude of this is just half of the nucleonic magnetic moments, so in terms of the nuclear magneton. So it's half of roughly 5.59 plus 3 minus 3.82, because of course the neutron magnetic moment is opposite to that of, so the neutron magnetic moment is anti-aligned with respect to its spin, whereas the proton one is aligned to its spin. So it actually subtracts, and so the magnetic moment of the deuteron, the magnitude is just about 0.88 times mu n. And this can be compared with the experimental value, which is about 0.857. So it compares pretty well. Now, of course, you can have a small admixture of the E2, and then there is a D state admixture. And so if you want to take that into account as well, the Gj for the 3D1 state is about 0.32, and this will reduce the M1 moment. So 0.87 will become somewhat smaller, and you can actually compute how much of admixture you need. So if psi is 1 minus a square root of that times the 3s1 plus a 3d1 state, actually this should be I think this should be a squared. So then you get a value which is a squared is of the order of 0.04. There is a 4% probability admixture of D state in the deuteron wave function. So even from the magnetic moment, you get a value like this. In fact, it will turn out that this value is very similar to what you get from the quadrupole moment of the deuteron. Of course, the caveat is that we haven't taken into account spin orbit effects, relativistic effects, meson exchange and so on. So, this is just from a very simple picture that you get the right ballpark figure for the magnetic moment of the deuteron. And you also, you can sort of understand that the small difference perhaps could be due to the d-state admixture. Okay, so now we come to E2 and M1 moments of the deuteron measured by so-called molecular beam method. So, you have these molecules coming out and making a molecular beam. They come out from something that is at a small temperature, 80 Kelvin, and then you can look at the fine structure of these molecules. You can resonantly excite transitions in these magnetic substrates, from these magnetic substrates, and there are two ways of doing this to get these frequencies, to get these energies corresponding to those resonances. One is you can actually keep a frequency which is fixed and you can change the magnetic field. This is what was done by Rabai and his group in Colombia, and this is the reference 1939, and this is a short letter paper and this is the full paper in Physical Review. So, from these experiments they could get the quadrupole moment, but of course the dominant effect is due to the magnetic moment of the deuteron, and they got that to about 0.853 times the nuclear magneton. And importantly, the paper is also titled the quadrupole moment of the deuteron. They get the quadrupole moment of the deuteron to be about 2.73 E times mb. Okay, so mb has the dimension of length squared. This is the charge of the electron. So, from this they concluded that the quadrupole moment of the deuteron tells us that this is a prolate shape, a small prolate deformation of the deuteron with density distribution, and which is the long axis is aligned to the spin of the deuteron. So, this depicts the spin of the deuteron, and this is aligned with respect to the prolate axis, the long axis of the prolate deformation. So, here you can see that these are resonant transitions. So, the beam intensity shows dips corresponding to the resonant transition, and what is varied here is the field. This uses the Rabai's molecular beam method, in fact something for which he got the Nobel Prize. Okay. So, this is done in this case for the hydrogen as well as, so this is hydrogen in the molecular hydrogen H2, and this is deuterium in molecular deuterium gas. There is another way of actually measuring this electric quadrupole moment of the deuteron, and this in fact was proposed and the experiment was done in reported in 1985 by Knudsen and Kamerad. The idea is that you can polarize a deuteron. The deuteron has spin 1, so you can polarize it such that you can get a population in the mz equal to plus and minus 1 states as compared to m equal to 0 substates, and then you can scatter these polarized deuterons of lead 208. Now, why do you use lead 208? Because it has a large electric field close to the nucleus. So, the deuteron, if it is it has a quadrupole moment and it is polarized, then depending on the direction of this polarization with respect to the scattering plane, you will find differences in scattering. Okay. So, this the schematic of this experiment is shown here. There is a beam of deuterons, a polarized beam of deuterons coming in, then there is a target of lead 208, and then this scatters at backward angles. So, this experiment is done at a very low energy, just 4 MeV, well below the Coulomb barrier, which is about of order 10 to 12 MeV, and then you have monitor detectors on either side, left and right, and then you have a Faraday cup. And if you want, they have an arrangement to also monitor the tensor polarization, the polarization of this beam. So, you have helium cell from which the deuteron beam scatters, and these are the so-called polarimeter detectors, and you can monitor the polarization this way. So, the backward detectors, there are two of them. So, if the beam moves slightly or it changes the angle, if you take the square root of these count rates to first order, that effect vanishes. Okay. So, this is a typical energy spectrum of deuterons scattering off the lead target, counts versus energy of the scattered particle. You can see a nice peak arising from the elastic scattering of deuterons versus the lead. At backward angles, of course, you have other contributions, and these are actually shown scaled by a factor of 64 or so. So, they are quite large, but still this peak is separated enough that you can identify the counts from lead scattering. These are this background is coming from various kinds of transfer reactions and so on. So, what is plotted here is the so-called tensor analyzing power. So, as a function of the center of mass angle. So, you can also rotate these detectors, and you can see that this they have done this at 4 angles, 130, 140, 150 and 160 degrees, and there is a certain dependence on this. It is a very small effect. It is a 0.05 to 0.1% of the order of 0.05% effect, and so this arises because, of course, there is a difference in scattering from the m equal to plus minus 1 states as compared to an m equal to 0 states. Okay. So, the T to 0 is about 6.2 10 to the minus 4, and from that they infer a quadrupole moment of 0.29 or so E Fermi squared. Okay. The error is mainly from the counting statistics and dead time correction. So, in principle, if the experiment goes on for a longer time, if you have a larger array of detectors, for instance, and count for longer, you can reduce this error bar and then go to the next limit that you will reach, which means systematic errors and so on. So, this is a very different kind of experiment, and it gives you roughly the same quadrupole moment from this experiment. Okay, then I will just mention also the E1 polarizability measurement of the deuteron. In this case, of course, again a similar experiment is carried out. You go sub-coulomb, you go below the barrier and you scatter the deuterons of lead target. So, in addition to the Coulomb potential, which we know is 1 by r, Ze squared by r, you have because of the large electric field, and you can polarize this deuteron because the binding energy of the deuteron is small. So, you expect that in a large electric field, you can polarize this, you can get a transition electric dipole moment of the deuteron, and then you can measure the effect of this because it adds to the potential, and it gives actually a 1 by R4 potential. Okay. So, as compared to the 1 by R potential, you get a 1 by R4 potential. So, what happens is, and this is opposite in sign, this is Coulomb potential is repulsive, whereas this is attractive. So, you can see that backward to forward ratios, if you measure, this ratio should show a deviation from the constant value as the energy approaches the Coulomb barrier, because then at the Coulomb barrier you are the closest to the nucleus. So, this measurement has been carried out again by the group of Knudsen, and this is the 82 reference. So, if this ratio, which is just n of E of theta 1 divided by n E of theta 2 by, let us say, so this is a backward to forward ratio that you can plot, and this should be 1 if there is no dipole polarizability, or if dipole polarizability is equal to 0. In fact, they measured this, and so this is a pretty large effect. This is almost like 3% close to the Coulomb barrier, and from that they calculate the polarizability to be about 0.7 plus minus 0.5, and the best calculations, of course, are about 0.64. So, there is a difference, but within error bars this agrees, and so this is another electromagnetic response of the deuteron that has been measured fairly accurately. Now, just because we are at it, I would just like to also say that the same idea of looking for a 1 by r to the power of n potential in a nucleon nucleus interaction was looked at, and this is the reference 87 Pramana reference. The same idea, you look at the forward scattering is dominated by the Coulomb potential, which is 1 by r, but the backward scattering could have a small contribution if there is a long range interaction like a van der Waal interaction, which of course falls much faster with distance. So, we have looked at, for instance, a 1 by r7 potential, and we obtained a limit lambda 7 less than 50. So, we looked for a small deviation. We made sure that the apparatus is sensitive to polarizability of the deuteron. So, this experiment was carried out with the deuteron as well, and it showed the right effect. And then we did this for a longer time with protons. So, proton on lead, and this appeared to be flat. So, this is the kind of dashed line shows of the order of lambda 7 equal to 100. So, using the data that we had, we could put a bound of lambda 7 less than 50. So, there does not exist a color van der Waal force which goes like 1 by r to the 7 with the constant. We can rule out this coupling lambda 7 to be greater than 50. Okay. So, it could be less than 50, then we would not have seen that effect. So, this is just a, I thought this would be interesting because it uses the same idea of Knudsen to measure both the quadrupole moment of the deuteron as well as the dipole polarizability, electric dipole polarizability of the deuteron. But this is trying to get a handle on whether or not there are long range interactions in the nucleon-nucleon potential. And as far as we can tell, there aren't such potentials at the sensitivity that we have. Okay. So, in summary, we have discussed the main features of the deuteron using just a simple NP potential, and some of the important features of the deuterium related observables such as the magnetic moment, the quadrupole moment, the dipole polarizability, electric dipole polarizability, and a possible long range interaction, which is a little more general nucleon nucleon potential. Is there a long range? So, these are some of the things that have been discussed in this lecture. Thank you.